Okay, looks like we're live. Hey folks, welcome to today's talk on PyTorch Expert Exchange. We have with us today Akihiro, who is a software engineer at Kumo.ai, and he's also a core contributor to PyTorch Frame and PyTorch Geometric, and has also been a maintainer of PyTorch Lightning in the past. So he's no stranger to the PyTorch ecosystem, and we're really excited to have Akihiro here and talk to us about PyTorch Frame. So just a reminder, if you're watching this on LinkedIn or YouTube, please feel free to ask any questions in the comments and we'll try to get to them towards the end of the talk. With that, I'm going to hand it off to Akihiro. Please feel free to take it away.
Thank you. Thank you for the introduction. Yes, I'm very excited about presenting PyTorch Frame today. So the title is Multi-Modal Tabular Deep Learning with PyTorch Frame, and I am a software engineer at Kumo, working on the ML team. And okay, let's get started. Oh, by the way, this is a Python library that you can use. You can install it with pip install PyTorch Frame. And today I'll talk about tabular learning and specifically challenges in modern tabular learning and why we created PyTorch Frame and what is PyTorch Frame. And then we will extend PyTorch Frame to use cases with multiple tables. And first of all, in the tabular domain, basically tree-based models are dominant, but they come with limitations. For example, they're focused on numerical. Oh, okay. They're focused on numerical and categorical features, where modern tabular learning. Oh. My voice is okay, hopefully. Echoed. I hope it's okay, but let me know. So modern tabular data have text and images, and also so tree-based models don't directly work on those features directly. And another point to note is that integrating tree-based models with deep learning models is not trivial. For example, if you want to use big image extractors or text encoders, using them with tree-based models is not trivial. And so to address these issues, we created PyTorch Frame with colleagues at Kumo. And it's fully open source, so you can use it as well. So PyTorch Frame is a modular framework for tabular learning, and it supports multimodal features such as numerical, categorical, timestamps, images, text, and so on. And also the design, how it's designed is very flexible, so that PyTorch Frame can express existing good models out there, like trumped, Excel former, FD transformer, and so on. So we have 7 or 8 built-in models, so you can try them out without knowing what they are. So please give it a try and let us know what you think. And PyTorch Frame also supports integration with foundation models and also GNNs. We will cover this in later slides, but you can basically use OpenAI API to get embeddings for your text columns and so on. Also, you can train your open source model locally at the same time as training your tabular model. And also, we presented PyTorch Frame at New Rips workshop last year, and we've got the best paper award. So this is an exciting project. And so when you have raw table data, the first thing PyTorch Frame does is data materialization. And during data materialization, PyTorch Frame is mainly one thing. It encodes a raw data frame into tensors, because subsequent models are written in PyTorch, so we want to use PyTorch tensors. And also, it also additionally computes statistics such as mean, standard deviation for numerical columns, and it also computes count of category occurrences for categorical columns. These stats are useful for fitting missing values at later stage. And so on your right, you see raw data frame and tensor frame. And so the data, this stage is responsible of producing a dictionary of tensors called tensor frame, and which is basically a mapping from column names to tensors. And one thing to note is that it doesn't just hold normal PyTorch tensors, but it also holds sparse features in our data structure called multi-nested tensor, which we will cover as well later. And okay, so PyTorch Frame has conceptual column types, and we call them semantic type. So semantic types could be numerical, categorical, multi-categorical, timestamp, or embedding text things and image columns. And you could also imagine that you could possibly add postcode column as well. So and PyTorch Frame basically encodes these columns into tensors, and we support all of these column types, semantic types. And I will briefly explain what the difference is between these two semantic types. So in PyTorch Frame, there are two ways to handle text columns. One is to pre-encode text during data materialization once to avoid computing the same embeddings again and again during training. So this semantic type is called text embedded. So this will only run once. So you can use OpenAI embeddings, or you could run Hugging Face models locally and once at the beginning of your training, and then reuse that across training later. Another way is to also jointly train your text models with tabular models. And how this option, text tokenized semantic type, works is that it first tokenizes text during materialization once, and then later in modeling part, you will fine-tune embedding, train embeddings in encoder part. So you can learn, in PyTorch Frame, you can do both freezed, you can use freezed embeddings as well as you can jointly train embeddings as well. So that's the difference between these two. And another thing that I want to point out was these two semantic types, which have varying length in nature. So multi-categorical column might have one user. In one table, they might have product tags column, and the number of tags in each cell might differ from each other. And also, it applies to text tokenized as well. So this is how we handle sparse features. So we provide a multi-nested tensor to store variable length features efficiently. And with this structure, when you store sort of these varying length features in a dense tensor, the size of the tensor will be n. N is the total, is the number of cells. In this case, 6. And max entries would be like, in this case, 4, 0, 1, 0, 1, 2, and 3. So max entries would be 4. And size D type is, in this case, these all values are in int integer. So it might be int 64. But when the number of max entries is very large, it's inefficient to store them as a dense tensor. So we have this is kind of similar to what TorchFrame has. They also have jagged tensor, key jagged tensor thing. That's quite similar to ours. And so with this, you can store them very efficiently. And so now I talked about data materialization, data preparation. Now you have to model your tabular model. So we provide the way we structure it, modeling part is divided into 3 stages. One is encoding, and another one is column-wise interaction, and the last part is decoding. So the first part is encoding. It basically embeds each column independently. So for example, it could be imputing missing data, or normalization, or embedding lookup for categorical columns case, and cyclic encoding and position encoding, and so on. And the second part is column-wise interactions, which basically mixes each column representations across columns to get the final embedding per row. And this is the last part of the modeling, and it's called decoding. Decoding, it summarizes column embeddings to obtain the final raw embeddings. It could simply be weighted sum of column embeddings. So n by c by f tensor will become n by d. And these 3-stage model architecture is expressive enough to cover existing models, such as trumped, Excel-former, and FD transformer. So this is the code. It's super easy. So there are 3 parts, as I mentioned, and one part is encoding part. You can specify what semantic types you have in your data, in your table, and which encoders to use for those columns. And the second part is, in documentation, we call convolutions. But you can apply L times, and on the left num layers times. You can basically plug and play just like you do in pure PyTorch, Torch NN, or Torch Geometric.nn. And finally, decoding part looks like this. This is simplest case. It's just linear layer applied to get the final embedding. And this one didn't fit in my presentation very well, but I just wanted to sort of show appreciation for a lot of cool work by PyTorch team. So I wrote an example. You can run this as well, but there are many examples, and this is just one example of that. And I wanted to showcase how torsion compile and DDP improves your performance. And all I did was address, if you know torsion compile a bit, to get the best performance, you might want to address basic stuff like addressing CUDA synchronizations and so on. And also, when you're using torsion compile, you want to address as many graph breaks as possible to let the compiler do the best job. So in this case, even on a single GPU, it's about 4 times faster. And then by using 4 GPUs, it's I don't know, a lot faster. So this is super exciting. And so that until this, it was about single table. But usually in real world, you have many tables connected with each other. For example, e-commerce case, you will have users table, sales table, products table, and they're connected with each other with foreign key, primary key relationships. And real data may have many more tables in your relation data. And relation data is essentially a graph. So, for example, well, not an example. So what I mean is that in the graph, a node denotes a row in a table. It could be a user in users table, or a certain product in sales or products table. And an edge denotes a primary key, foreign key relationship between nodes. For example, users ID point is connected with sales.user ID column, and so on. And nodes can also have features. In this e-commerce case, user features might be age or postcode, where they live, or sign up date, and so on. Product features might have price, category tags, image rating, and so on. And so once we treat this sort of treat relation data as a graph, a large scale graph, you can do normal graph ML. For example, what people are interested in might be predicting users attribute like age and so on. Or on your left, you can see lifetime value. It can be seen as temporal regression task in graph. And item recommendation task problem might be can be considered as temporal link prediction, and so on. So yes, and one way to do ML on such data is to apply graph neural networks. This is applying GNNs onto these large-scale data is very nice because you don't have to do feature engineering at all. What people do normally is merge and join different table so that you will have a single table, and then feed the single table into some tree-based models. But that will drop some information, and it's not a raw data. So you don't have to feature engineering with GNNs, and you so because GNN training, you will use temporal sampling so that whenever you sample a node and a subgraph around it, you don't sample future nodes. and because basically the graph representation is a mapping from your tables in your relation database, so there's no loss in information. And yeah, quickly to explain how you do is step one is sample a subgraph. So if you're interested in whether this user will churn or not, you sample the node and sample neighboring nodes around the interested node. And then next, you will compute node embeddings for nodes in the subgraph and use that node embeddings as a node features in GNNs and perform message passing across tables with GNNs. So all of these can be done with PyTorch Frame and also GNN library. Here we use PyG. And so the code looks like this. It's quite simple. PyTorch Frame part is now here. Instead of using one tabular model, you will have two models in this case. And then there's one new part, which is written with PyG to basically mix information across nodes in the graph. And this two header row is very my favorite feature from PyG. It uses touch effects to manipulate your homogeneous graph layer and convert it into heterogeneous layers with just calling this function. And you can learn more about these sort of PyTorch Frame plus PyG code in these papers and the repositories that we published. And for context GNN paper, we will be presenting in Singapore at ICLR. So hopefully, if you have any questions, please let me know at the conference as well. And this is the final slide. So we covered, so PyTorch Frame covers support for multi-modal features, LLMs, as well as GNNs integration. And your next steps will be to go to the repository and run examples and let us know what you think. That's very valuable, and I want to expand this open source project. And please do check out Workbench and Context GNN if you're interested. And also, please do contribute. This is exciting project, and we already have 20 or 30 community contributors. So that's quite impressive. And also, please join PyG Slack. And a quick roadmap would be, I'm open to ideas, but we could add more layers or more tabular models to PyTorch Frame. We now only have 8 built-in models, and then 2 sort of possible things to do is to integrate nested tensor from PyTorch. They added a new thing, so and it looks good. They added a jagged layout to nested tensor, which might be used for us as well, and also integrate FBA gem kernels. I think some of them might be useful for us as well. So yeah, that is all, and thank you for coming today. And yeah, thank you.
Awesome. Thanks so much, Akihiro, for that talk. It was great to hear PyTorch Frame and details about what you support, what your roadmaps, and how you use PyTorch. So I guess, like, as we're waiting, maybe one question, like a general question from me, is about like any feedback or thoughts that you want to share with the PyTorch team on what worked well for you, what didn't work as well, and what you would like to see differently?
Oh, well, this is kind of maybe off topic, but at Kumo we use GNNs a lot, and I'm trying to adopt Torch to compile, but there seems to be some issues around it. The more friendly explanation of why Torch to compile failed and so on. So that might be one sort of comment.
No, that's definitely useful to know. I'm happy to follow up with you after on
Yeah,
that.
thanks.
Yeah, I think we also have Joel on the call, who actually built nested tensors in PyTorch. I don't know, Joel, if you want to jump in and ask any questions.
I don't have any specific questions. I just thought it was cool that you called it out as a possible adoption target. So I'm happy to work with you on that.
Nice.
Awesome. Yeah, looks like there's a long question from the comments. About any overlap with Daft.
I have no idea. Need to check after this stream. But we're very open to collaboration as well. Yeah, since exciting. Sorry, I don't have much information about Daft. And yeah. Curious how graph NNNs do when benchmarked against traditional decision tree algorithms. We have a very thorough benchmark results on the PyTorch Frame repository against such models. And I think graph NNs, I see. So when you use traditional decision tree algorithms, you have to sort of squash multiple tables into one by merging multiple tables, and you essentially lose some information. And also you have to manually craft features as well, as I covered in the talk. And at Kumo, we exactly do that. We apply graph neural networks on relation data, and it's working perfectly great. And you will find results on the repository as well. What was the initial motive problem statement which led to PyTorch frames from scratch? Could you share some insights on how it all started when you were building graph embeddings using any PyG supported algorithms? We sort of had that in Kumo because we believe that GNNs on relation data would work very well. And also we wanted to have rich node embeddings from those rich columns, such as images and text columns. And to do that, there are some libraries like PyTorch Tabular, but they're more higher level, and it's good for like for those who don't want deep into, who want to go into modeling part. So but as far as I know, there weren't such this level of, it's not to level PyTorch Frame is, but yeah, I don't think there are such library that allow us to get rich embeddings to feed into GNNs.
Well, I think that's all the questions. Do we have any more questions from the comments? All right, looks like that is all the questions from the live stream. And we are right on time. Awesome.
Nice.
Cool. Thanks again, Akihiro. It was
Yeah,
great having
thank
you
you for having
here.
me.
And look forward to continuing the conversation with you on some of the other things we discussed.
Yeah, sounds good. Yeah, thank you for having me.
Bye.
Bye.